it on the right side of our equation, right? We're normally not having to play with the left side of our. It's just always y equals on the left. But now we're going to have to kind of go through calculus procedures on both sides of the equations. So it just makes our problem a little bit longer to get through. So when we solve different equations, some of the things that we need are kind of out of place. So we need to be able to get our equation into their proper places before we move into our calculus step. So this is called the separation of variables. We want to rearrange our equation with y and dy, our dependent variables, on the left. And then our x's and dx's are independent variable on the right side of the equation. So also, whenever you see this notation dy dx or du over dx, whatever's in the numerator is your dependent variable. Whatever is your denominator is your independent variable. So a lot of times it's y and x, but sometimes it could be like w and t. So yeah, it's always dependent over the independent. So the first step I like to always do is cross multiply. So when I cross multiply, it's not going to solve the problem for me, but it will get some things in their right places. So so when we cross multiply, we're just multiplying the diagonals together. So now we have y dy is equal to 2x dx. And as you do this, the thing that I want you to pay attention to is that you are at least going to make some progress because the dy and dx's are going to always be in their right places. So think of these as your anchor variables. We need our dy on the left in the numerator. We need our dx in the numerator and on the right side. And then the other pieces may be out of place. It's okay to have y's or x's in the denominator, but we don't want our dy dx in the denominator. It doesn't quite fit the form that we need. So after we get these dy dx's in place, then we can ask ourselves, do we have our x's and y's in their right places? This one already does. The y's are together. The x's are together. And then we can move into our antiderivative process. Normally, we just worry about the right side, but now we also have to do our calculus procedure on the left side as well. So our next step, we're going to take our antiderivative on both sides of the equation and basically treat each side as its own problem. So y dy, we go through power rule. So power rule for y is just y squared over 2. We'll treat y the same way that we would do x's. And then 2x dx, we also do power rule here. And then plus c. This is the new packet if you guys came in. I can pick up. Okay. Left side and both the left and right side, they both produce their own plus c. But we're just going to merge the c's together and just write it once on the right side. Once we're here, we're going to do a little bit of cleanup. I'm just going to move that, get rid of that 2 on the left side. We want to, usually we want to get that left side as clean up as possible. So what I can do is I can multiply both sides with 2. And move that 2 over to the right side there. So the 2's cancel out. I'm left with y squared, distribute the 2 through. Well, the 2's cancel out here, but the 2 distributed will give me 2x squared. And then if you multiply the 2 through, technically, yes, it's a plus 2c, but anything that we multiply, divide with c, it's just still a constant. So we don't have to put that 2c there. You just know that the c is just going to absorb anything that comes its way. So we're still doing the same thing as before. We're still taking our derivative level and trying to bring it up to the function level. But it just looks more complicated because we have to do calculus on both sides of the equation rather than just the right side. So number 2 here, solve dy dx equals x times 1 plus x. This is some derivative equation that we want to bring it up to the function level. So my first step is get my fractions to show up. I want to be able to go through my cross product stage. Again, when I cross multiply, I am getting some things in place, but not everything. Usually it's not everything in place, but you will get your dy and dx's lined up. Oh, and also when you're solving differential equations, we typically don't want to undo the parentheses. Sometimes the parentheses in problems are trying, they're trying to, we have to undo them so that we can move into our power rule process. But when you're solving differential equations, typically the parentheses are there to help you. They're there to help you keep things organized. So we typically don't want to lose a set of parentheses when you're solving a differential equation. All right, next step, we're going to cross multiply. And again, the whole purpose of cross multiplying is we want to get our dy and dx's lined up. I kind of think of this as my anchor step. I want to get those variables in their right place. So 1 times dy is just dy. Distribute the x through, I get x times 1 plus y dx. So whenever you go through cross multiplying, you're going to at least have these 2 in their right places. And we're not going to move them. These are, we want dy on the left in the numerator. We want dx up in the numerator on the right side. So now the only thing that we have to worry about is, are these in their right places? So what do you see? Do you see x's together on the same side and y's together on the same side? Something is out of place, right? What's out of place? Yeah, but that y is attached to the 1, so this is gonna go together. Okay, so if you want to move the y, you want to move the parentheses along with it. So the way we move it is we're going to divide it to the other side. So we're going to divide that 1 plus y to the other side. So when we divide that 1 plus y, remember, anytime you divide something from the numerator on one side, it's going to end up in the denominator on the other side. So this ends up looking like this. dy over 1 plus y is equal to x dx. Okay. Now, do we have full separation of variables? Okay, we do, right? X's are on the right, y's on the left. It's okay to have y's in the denominator, x's in the denominator. I see some students do this where they get to this point, they don't feel comfortable with this, so they move the 1 plus y to the numerator, and then that changes the whole setup of the equation. So we're no longer solving the problem that they want us to solve if you're just randomly moving your variable to the top. So we have full separation. So now we can move into our integral process. This is basically a small little u substitution problem. Your u value is the 1 plus y. So I make my substitution. This is really 1 over u du, which is natural log. So I can turn this back to natural log. And then I can bring my 1 plus y back into my antiderivative. So the result of that left side ends up being just natural log abs value of 1 plus y. If you recognize the fact that it's just a little u substitution with 1 over u, you can jump from here to here if you feel comfortable with that. Okay, now the right side, integral of x dx, this is just power rule. So x becomes x squared over 2 plus c. So everything is at the function level now. The only thing that's left to do is we have to solve for y. So the rest is just algebraic steps to get us to the point where we can solve for y. So let me walk through this. There's quite a bit of algebra left to get to y. So the idea is I want to get to that y, but y is stuck inside the natural log. I'm going to raise both sides with base e because I know e and natural log have a way of undoing each other. So I'm going to do this. I'm going to exponentiate both sides, raise both sides up as exponents. And anything I do to one side, I can also do to the other side as well. So now my original equation, they're all sitting up as exponents. But the reason that we're doing this is because we're trying to clean up this left side. We want to get that natural log to go away. So now e and natural log are canceling each other out because e raised to the natural log is just the expression that's left over. So this goes away. Now this is e to the x squared over 2 plus c. This is all sitting up in the exponent. I want to remind us of a exponent property that says if I have a to the m plus n, I can break it up into a to the m times a to the n. I'll show you why that is helpful for us. I basically want to get that c away from my expression or have the c be its own thing. So I'm going to make this e to the x squared over 2 times e to the c. Now, e is a number. C is also a number. So if I have a number raised to a number, this whole thing can just be some constant. Let me use the space below here. So abs value of 1 plus y is equal to e to the x squared over 2 times c, because e to the c is just some constant. And also, we've changed the plus sign in the exponent. When you have something added in the exponent, it comes down as multiplication at the base level. So this plus c is now times c. Okay, almost there. I'm going to pull the coefficient out in front. I like to have that coefficient in front of my variable. And then we're going to now drop the absolute value. Anytime you drop the absolute value, we need to represent with a plus or minus on the right side. So 1 plus y is equal to plus or minus c e to the x squared over 2. Yeah, I know there's a lot going on, but there's a lot of these types of problems. And then once we get comfortable with the process, it'll eventually come to us. But just right now, I just want you to kind of follow along. The plus or minus, c is a constant, so it can take in both positive and negative numbers. So we'll just let that plus or minus kind of get sucked into that c there. So we'll have 1 plus y is equal to c e to the x squared over 2. And then our final step, we just want to get that y by itself. So we'll subtract 1 to the right side. Y is equal to c e to the x squared over 2 minus 1. This we call a general solution because there's still a c in our answer. Next problem, they'll ask you for a specific solution. And to do that, they will have to give you an order pair. If they give you an order pair, they can ask you for a specific solution, which just means plugging the x and y, solve for c, get a number for c, and then update the equation with the c replaced with a number. Okay, number 3. Okay, we're going to spend quite a few days on this. Okay, so there's a lot here, a lot of algebra, along with the calculus. So we're not going to rush through this. We'll take our time. So we'll have plenty of days to practice these problems over and over again. All right, so number 3 here, find the general solution, then find the particular solution. Anytime they ask you for a particular solution, they have to give you an order pair, and there's an order pair in this process. So the first thing that we're going to do is we want to rewrite that y prime. Y prime is the same thing as dy over dx. So we're going to rewrite that y prime as dy over dx so we can kind of have the things that we need, the things that we want to kind of line up. But I like to do this first. I'm working towards getting 2 fractions to equal each other because I always want to cross multiply to get my variables lined up. So I'm going to subtract that 2x over first. And then I'm going to create my fractional values here. Now, y prime is dy dx, so I'm going to rewrite that as a fraction. So 3y dy over dx. And then the right side, I'm going to force a fraction as well. Next up, cross multiply. Again, cross multiplying is just to get our dy dx's in their right spots. We're not going to be able to guarantee the x's and y's are lined up yet. So this is just the first of potential more steps we got to do. I like to have cross multiply in a way where your dy will end up on the left, and then your dx is on the right. So as you do this, you're going to be able to get something accomplished. What you're going to get accomplished is that your dy and dx's are going to be lined up. These are going to be your anchor variables. You want these to be in place first. Now that those things are in place, we can ask, are the other things in place? Are the x's grouped together? Are the y's grouped together? Yes. All right, so this one already has full separation. That's nice. We don't have to do any more movement. But there is one thing that I want to talk about is that we want to leave this left side. I like to leave the left side as minimal as possible. Whatever that doesn't need to be there, I would like to move. So that 3 doesn't have to be there because I can just move that 3 over. Eventually, we have to move the 3 over anyways. So I'm just going to do it now. If you leave it over on the left side, it's okay. But I just like to get my equation as cleaned up as I can before I move on to my antiderivative step. -2 over 3, I can just think of that as a coefficient in front of my variable. Oh, there's a new packet behind you there. Now, full separation of variables. Now we can do our antiderivative step. Both of these look like nice power rule problems. Power rule here, power rule here. let me try to get y squared by itself. I'm going to multiply everything third by 2 here. This is good enough for us to call this a general solution. So again, general solution has a c. Well, we could do plus or minus, but we'll leave this as y squared. General solution has the left side as cleaned up as we can make it. And then there's a plus c, or there's a c in our general solution. So now let's move towards a specific solution or particular solution. And we're going to start involving that order pair, 1 and -2. We're going to plug that in, solve for c. And once we solve for c, we can update the c with the number that we found. Okay, so now our next step, we're going to plug in 1, -2. 1 in for x, 2 in for -2 in for y. -2 squared is 4. -2/3 times 1 squared is -2/3. If I add 2/3 to 4, that's same thing as 12/3 plus 2/3, which is 14/3. I have my c value. I'm going to update my c value with the number that I just found. So y squared is equal to so I am close to my specific solution. There's one final step that we can make is let's get it down to y equals. So to get to y equals, I'm going to take the square root of both sides. Plus or minus will show up. Now, these are actually two solutions here. These are two separate functions. So it's either this or it's this. And that the way that we can tell between these two equations is we want to find the equation that actually has this ordered pair living in it. And the easy way to tell is looking at the y value. If I plug 1 in to both, I got to get a -2 in return. The only way I get a -2 out of a square root is if there's already a negative sitting in front of it. So that order pair is going to tell me, the sign of that order pair will tell me which radical to choose. So we'll choose the -1. This is the one that if I plug 1 in, there's no way that this can give me a -2 because there's any square root will turn everything to positive here. So the only way I get a negative is if there's already a negative living outside of my function. Okay. So look at the y value. Look at the sign of the y value. Okay, next page. Find a general solution for y prime equals 6 cosine of pi x. Then find a particular solution. So let's go ahead and rewrite that y prime as dy dx. My first goal is to get my dy and dx's lined up. So I'm going to force that 1 in that fraction there so I can cross multiply. Again, cross multiplying is just to get the dy dx's where we want them to be. So if both sides are at the derivative level, we do want to take the antiderivative, but if you look, dy dx's, that's our goal, initial goal. These need to be in their right places. And now we can take a step back and ask, okay, do we have full separation of variables? Are the y's together? Are the x's together? And also, there's nothing that we need to move. The left side is as bare and as minimal as we can make it. If there was a coefficient in front, then I would typically want to move it to the right, but this is ready to go. No need to move anything, so we can move into our calculus process. Left side is just a nice power rule, but the right side, there's a little bit of u substitution here. That pi x, we need to take care of that. So let's take care of that here. So u equals pi x. du over dx equals pi. Pi is just the number. Cross multiply. Replace pi x with u, replace dx with du over pi. I can pull the pi out in front as coefficient. We know the antiderivative of cosine is just sine. So the right side required more attention, so I went there first. 6 over pi sine of u. Let's bring the pi x back. And then the left side is just y squared over 2. So I'm going to update my both sides here. Everything's at the function level now. We took the antiderivative on the left. We took the antiderivative on the right. We went through u substitution. We converted cosine to be in terms of sine, and we brought back our x. It says to find a general solution, so we can just multiply through it by 2 here. Let me just get that left side a little bit more cleaned up. Having that y squared is fine if we just look for a general solution. Again, the 2 will distribute to both these terms. Technically, it does distribute to the c, but 2 times c is still a constant, so we normally don't have to do anything with that c. So this is my general solution. Okay, let's move into our specific solution. 1 in for x, 2 in for y. The nice thing about sine of pi is just going to be 0. That's going to wipe this whole thing to be 0. So c is just equal to 4. Once you have your c value, go ahead and update where you initially made your substitution. So I'll put 4 in for that c. And we have to move into resolving that square root there. Hit the square roots, plus or minus shows up. And now we have a decision to make. Which one are we going to keep? So the hint is with the ordered pair, which one do you think we're going to keep? The positive or the negative square root?
Positive.
Because the y value is positive. And so I'm plugging in 1 and I want a positive 2 in return. The only way I'm getting a positive 2 in return is if the outside the square root is a positive, not a negative. So it's going to be this one. We want the equation that has the order pair 1, 2 in it. Okay, let me pick out some problems for us to practice for tomorrow's quiz. Let me create 1 or 2 for us to try. You can find any open space or scratch sheet or notebook. Okay, so tangent of 2x minus cosecant of x over 3. If you look, we have the new rules involving tangent and cosecant. They both are involving natural log, but it's more than an x, so we can't just jump into the rule. We got to do a little bit of use substitution here. Oh, there's separate u values here. I want you to see a pattern here that could maybe save a few steps if you don't want to go through a full use substitution for the easier problems. What's happening with this 2x? What's coming out of this process? What do you notice? It's the what of this number? Yeah, the reciprocal, right? It's the reciprocal of this number. It's the opposite of chain rule. So that's why, chain rule will be times 2, but with antiderivative, it's going to be times 1/2. The use substitution process is just to make sure that you get that coefficient. And if you don't want to lean on that shortcut, you don't have to, but just want to point that out to you where you could save your time here, especially if you have a nice linear u value where you can just jump from there to here. What do you think this will produce? 3, yeah. So it'll just produce a 3 because this is 1/3 here. It should produce a 3. So it could save a little bit of time with u substitution. For the easier linear u value. So just want to point that out if you want to use it. If you decide to use it, you don't have to go through a full U substitution, because I understand students, being able to jump from here to here without having to go through a full justification, and that's fine. But you only do that if you feel comfortable with that process. Otherwise, don't, do this step if you feel like you're going to make a mistake. Because a lot of students will do this. They will say, oh, they will do ×2, or they'll do ×1/3, but there's a little bit of adjustment that needs to be made. So. Okay, so now we're ready for our antiderivative rule. There's a coefficient associated with each of our U substitution. The way I think about tangents is sine over cosine. And I circle that cosine below because that's what's going to show up in my natural log. So 1/2 natural log absolute value of cosine of U, and my U value is 2x. Oh, I thought of this while going through the rules with fourth period, was that, typically we think of tangent as associated with a positive. So we typically forget to include a negative. So what I was thinking was, if you look at this cosine inside, right, once you establish its cosine, when we think of cosine, we typically associate cosine with negative because there's C there. So if you look at what's inside here, sometimes that can help us remember, oh, there's a C there. I'm going to put a negative in front. Okay. Same thing here. Cosecant becomes natural log. Cosecant of U plus cotangent of U plus C. And then cosecant also has C in it. This is going to produce its own negative. So that's part of the rule as well. So it becomes +3. And I'll bring back my U value. Now, I would still go through U substitution if it was like, x squared over 3 or 3x squared. If it's anything more than linear, then I would take the time to go through U substitution. But if you feel comfortable with like 2x or 3x or x over 3 or x over 4, you can just jump directly and just understand it's going to be the reciprocal that's going to show up as part of my U substitution process. Okay, let's do one more here. So hopefully you can see this and recognize this as an A to the U rule. U substitution, we're trying to make it turn into an A to the U problem. X's cancel out. 2 over -10 is -1/5. I want to make sure that we understand any coefficient with an exponential function is not compatible. We can't make this -3/5. Okay, this is its own thing. Even though this looks like just a 3 here, it's not really a 3. It's 3 raised to an exponent. So You can't merge them together. -1/5. And then the integral of a to the u is 1 over natural log of a times a to the u plus c. And then replace the u back in terms of x. So your quiz tomorrow, no calculators. Make sure you memorize the formulas. In addition to the derivative rule for power rule, natural log, e to the u, and then make sure you know your original 6 trig rules. Tomorrow morning, I'll do 7:15 morning review. I'll go over page 13 in your packet. All right, come get your phones.